Okay, let me write. Right. So what is Coulomb's law? It talks about the electrostatic force between two charges. So whenever we have two charges,
Oh yeah, it's like the gravitational constant F equals to G1 by G1. Sorry, Q1 Q2 by R square.
yeah, so that is just analogous to the gravitational force, right? So in gravity, if we have two masses, then there would be gravitational force of attraction. Similarly, if we have two charges, so there would be some force, electrostatic force, and that is called what we call Coulomb's law, right? That is described by the Coulomb's law. But there is a difference between electrostatic force and there is a crucial difference between electrostatic force and gravitational force. Can you tell me that? What is the crucial difference between these two forces?
Uh, Coulomb's law is about electricity and gravitational law is about gravitation.
Yeah, so
Like
that's
grav-
yeah, that difference is already there. But I'm talking about the forces. They look similar, right? So F is
yeah.
GM1 M2 by R square, and F is K Q1 Q2 by R square. Both looks similar, right? But there is one very important difference between them, and that is that gravitational force is always attracting, right? It will always attract two masses. But Coulomb force can be repulsive and can be attractive depending upon the charges, right? Right, Rishita?
Yeah, yes, sir.
So this is the Coulomb force, and this is a vector quantity. So if I add some direction to it, so this would be the Coulomb force, right? And if I put this thing in some medium, if I put this thing in some medium, so this will become F medium. This is in air. So this would become simply 1 by 4 pi epsilon naught. And then this would become, let me write it as, so this becomes simply epsilon, not epsilon naught. And then you have Q1, Q2 by R square. And this epsilon, this is the permittivity of the medium, and this is equal to epsilon naught K, where this K is dielectric constant. So Coulomb's law is dependent upon the medium also, right? So this will be 1 by 4 pi and epsilon naught and K and then Q1, Q2. Remember, this K is different, this K is different, right? So let me write it as K, and this is small Q1, Q2 by R square. So this is F air divided by K. This K is the dielectric constant. So the force in the medium decreases because this K is always greater than 1. Right? So this is always greater than 1. So this F medium is always lesser than the air. So Coulomb force decreases when we place it in the dielectric medium. This thing you have already learned, right?
Yes, sir.
And then you add, so then the other concept that we would be using is the equilibrium, right?
Sir, can you go up 1 second?
Oh, so do you want to note this thing? This you have already done in your CBSE portion, right? So,
Yes, sir, but it's like a summary kind of thing. So I note everything you already write.
oh, okay, yeah. Okay, so yeah, then you can,
Yeah. Okay. Yes, sir. Done.
yeah. So then you have equilibrium, right? So there are two kinds of equilibrium in which one is that you have one point is at equilibrium. And what are the question? depending upon this idea, that there would be two charges, right? Let's say Q1, Q2, you place third charge, and what is the position? So if you want to find out the position of the charge, so that this charge is at equilibrium. So these kind of question, right? This charge is at equilibrium. So these kind of question comes in one point is at equilibrium. Second kind of equilibrium is that the whole system is at equilibrium, right? So these are the two things you have already learned. So I will not talk about them in detail, right? In whole system is at equilibrium, what happens? So let's say if we have three charges, right? Let's say this is plus Q, this is plus 4Q, and let's say this is some Q charge. So if I say that this at this point F net is 0. So this is what case? Case 1 or case 2? What is this case? Yes. What is this case?
Case 1, sir.
Case 1, because only one point is at equilibrium. What is the meaning of equilibrium? At equilibrium, you have already learned in your 11th class that at equilibrium, all the forces cancel each other. So F net becomes 0, right? This is the equilibrium condition. So this is one part. And second case is that, this is case first. Second case is that, let's say you have three charges. Right, this is plus Q, this is plus 4Q, and then let's say this is Q. So at in the second case, all these points. So at here F net is 0, at here F net is 0, and
The
at
whole is case 2.
yeah, so this is case 2. So the whole system is at equilibrium, right? And have you solved this question? Have you used this idea to solve a question? So you,
Yes, last year, yes. This year we haven't done it yet.
and last year, so this in the equilibrium part, you must have done this question. So there was this question
Oh yeah,
that
yeah. We did this. We did this. Yes.
yeah. So in this kind of question, you had to find nature, right, position, and magnitude of the third charge. So this was the question. So this we had to find that what is this position, what is the nature, whether it is positive or negative, and what is the amount or what is the magnitude of this shock, right? So if I tell you that this is the answer that you get, right? This is the magnitude you get. This position you get is L by 3, and the polarity or the nature is negative. So this question you have done, right? Yes. Do you remember this question? So these are the
Yes.
good. So please revise this question. This is very important. If you don't understand, then I will explain this thing again, right? So if you have any doubt in this one, because this is very important question. So yeah, please look at this question. And if you face any problem, Amna ma'am has done this problem like this. So you are please revise this, and this is very important. So this will give you the idea of equilibrium. Now we have Coulomb's law, we have equilibrium, and then we add three topics or three concepts to it. So we have Coulomb's law, and then we have equilibrium, and then we add mechanics. So these are the questions that has been asked. Right, so this is the thing that we add. And what kind of mechanics we add? So in mechanics, we add tension, we add spring, and then we add, and this is also called SHM, and then we add, let's say, buoyancy. So these are the things that we add, right? So for all these things, you have to remember, what is free body diagram. So this thing we have discussed, right? This is the thing that you will need. Okay, right?
Yes, sir.
So tension, you already know that this arises due to the thread, or what we call a string. So this
Yes, sir.
is because string. SHM, in SHM, what you will have? So in SHM, the force would be directly proportional to what? Do you remember this thing? What would be the force in spring?
It's a way in spring force will be directly proportional to.
Yeah, yeah.
Uh,
So, how many people are joining? Okay, so yeah, let me just so in SHM, who joined and then who left? Okay, I guess we have to join some room, right?
yeah. I think yeah, it was yeah.
Oh, so I guess we have to join some room, right? Let me so if they assign some room, right, please join that. Okay. Yeah, and whenever you have any doubt, please don't hesitate, right? This rule you already know. So from 1 year, you know this rule, and please don't hesitate. I guess another person is. What is the room that we have to join? Should we join room one? Oh, yeah, he has joined room one. Okay, so that is, yeah, that's fine. Yeah, he's talking. Okay, so yeah. So you have forgotten. Then it's all right. It's all right though. So spring force.
Distance.
Yes, absolutely correct. So this is what you get,
So is
right?
it distance or displacement?
So both are same because we are moving in one direction. So if we are moving in one direction, so displacement and distance they are same, right? Motion in 1D. If we are moving in one direction and we are not returning back, so then distance and displacement they are same, right? So what is this
But then
spring?
why did you write minus x?
Yeah, minus x because this is against the direction of the displacement or whatever distance it has covered. So this is against the displacement, right? So let me just recall. So let's say we have this spring, and then we pull this spring. So let's say some mass is attached, and then we pull this string in here. So let's say we pull this string x distance. So we have pulled this string in here. Now this is the string, right? So in this direction, we have displaced this thing, but the restoring force, the direction of the force would be where?
It'll be the opposite to the
So
distance.
this, yeah, so this would be the restoring force, right? Or the spring force.
Yes.
So this is what we call the spring force. And this is the thing. This thing we have learned in the waves, right? Okay.
Yes, sir.
So then this proportionality constant we remove, and this is kx. And then we know that this F is MA. So this is kx. We remove or we take this mass in the other side. So this becomes k by m and x, and this k by m, what is it called? So this called omega square, right? So this is the idea of SHM. This is the idea of SHM, right? Clear?
Yes, sir.
And what is buoyancy? So buoyancy is that whatever mass is displaced, right? So if this is the block, this is the block which is put in the water on some liquid, and this displaces some liquid, right? So from the Archimedes principle, right, what is this? Archimedes principle. It says that the weight displaced would be equal to the weight of this thing, and then it will experience some buoyancy force, which would be in this direction. And what is this buoyancy force? This is volume of this thing which is dispersed, or this is in this thing, right? And then the density of the liquid, and then G. So this is F buoyancy. Do you remember this thing?
Yes, sir.
Yeah, so this thing we will also use. So this is the volume immersed in this liquid, whatever amount of volume which is immersed. So it will experience F buoyancy, and that is equal to this, right? So yeah, these are the things that we will use in our next set of questions. Okay.
Yes, sir.
Okay, so let us do some questions on tension, and this you have already seen. So let me, yeah, this is about equilibrium. This I will, right. And then this is about spring one. Okay, so let's do this question. So let us do a simple one first, because that thing you know already, right? So let's do that simple thing first, and then, okay. Oh, so this is about equilibrium, right? So that equilibrium.
Sir, I'm sorry, but this is a 1.5 hour class, right?
Yeah, yes.
Okay, okay, sir. Thank you.
Oh, what is the name that I did? Yeah, so let's do this question. Okay, so what again? I will repeat that. What would be the concept that we will be using? We will be using Coulomb's law. We will be using equilibrium, right? Coulomb's law, which means that force is KQ1 Q2 by R square. Equilibrium means that F net would be 0. And then we will use mechanics. In mechanics, we will use free body diagram. These are the things that we have to do, right? In mechanics, it will also have three parts. So one would be tension, the other one would be SHM, and the third one would be buoyancy, right? So these are okay. So these are the concepts that we will be using, right? In buoyancy, what will be the force? So this would be V rho G. And then in SHM, force would be minus Kx. In tension, that is due to strain. So this thing we have to remove. Okay, so now let us do this question. Right. So what is this question? So a particle of mass 1 milligram and charge q is lying at the midpoint of two stationary particles, kept at a distance 2 meter when each is carrying same charge q. Right. So we have a particle of mass 1 milligram and charge q is lying at the midpoint of two stationary particles. So these two stationary particles are kept at a distance 2 meters. Right. So let's say that we have two charges or two particles. Right. These are the two particles. And in between this thing, we have some stationary another particle which is of mass 1 milligram, right? And then this one has also charge q, this one has also charge q, and this one is also charge q, right? These two are 2 meter apart, so this middle one would be 1 meter apart from each other. So in all these questions, diagrams would be very important. And if we understand the diagram, then all the things would be easy, right? So, yeah. So this completes this portion, right? So this diagram completes this portion, which means that this Q is what? This Q is what? Because if this is stationary,
It's
if it, yes, please think about it and tell me. If it is stationary, then what is happening to this thing?
it's at equilibrium.
Absolutely correct. So if this is stationary, which means that this is at equilibrium, right? So this is at equilibrium. And if we are not applying anything to it, if we are not providing any other thing, so this will remain in this position. Now what we are doing? So this is initial condition, initial case. Now what we are doing is that, so in the second case, what we are doing is that if the free charge particle is displaced from its equilibrium position through distance x, right? So we are displacing this thing at some distance, let's say in here. So we displace this thing. Right, so this is the displacement that we have done. So earlier it was in the middle. Now we have displaced this thing in x meter. Okay, this is not visible, so let me choose another color. So we have displaced, this is 1 meter, and we have displaced this thing x meters, and this distance is 1. This is the charge, this is the charge, and now the charge has displaced to what position? The charge is now here. This is the charge, right? So initially it was here, and we have displaced this thing in here. So this is the position of the charge. Is it clear?
Yes, sir.
So now if I draw the diagram, this diagram clearly, so now we have this case. Right, so this distance is how much? How much is this distance?
It's less than 1.
No, we have this, so this is 1. This was 1, and then we have displaced this thing in here at x distance, so this is x. So now what is this total distance?
1 plus x.
1 plus x, right? 1 plus x. And what is this distance? Yeah.
1 minus x.
1 minus x, absolutely correct. So this is the distance. Now, so now this is, so now will this thing will be at equilibrium? Will this thing would be at equilibrium?
No, sir.
No, so now it is not at equilibrium. So which means that F net is not 0. So let us find out what is F net, right? So now let us solve this thing, right? So effective diagram. This is effective diagram. So now let us calculate, because this point is not equilibrium. So let us calculate the force at this point. So how many contribution would be there at this point? How many contribution would be there?
Where, sir?
At this point, how many contribution would be there? How many forces would be there?
2.
2 forces, right? One would be due to this one, and the other one would be due to this one, right? So let's count.
Yes,
Let's count this one. Let's count this one, and let's say that at this point, And let's say that that is F1. So F1 would be right hand side, away from it, or towards this Q charge. What should be F1? Towards 1 or away from 1?
F1 will be away from 1.
Away from 1. Absolutely correct, because the force is repulsive. Same charges, force is repulsive, so it will repel this thing, right? So let me write it in here. This is F1. Good. Similarly, what would be F2? Towards this Q or away from this Q?
Away from Q.
So again, it would be in this direction. Right?
Yes, sir.
So F net would be how much? If I write F net would be, this would be F1 minus F. Is it clear to you why why I have taken, why didn't I take F2 minus F1? Why I have taken F1 minus F2? Is this part clear?
Yes, sir. F1 is the force of F1 is bigger than F2.
Okay, so no, not that, because I have assumed that F1 is I hat, right? F1 is I hat and F2 is minus I hat. So if I add those two forces, then F2 would be negative. So that is why, right? Because F net is the resultant, right? This is the superposition principle that we have learned. So F net is F1 plus F2 plus F3 and so on. This is the superposition principle you have learned, right? Now F1,
Yes, sir.
F1 is I hat and F2 is minus I hat, right? So this would be, oh, why did I write this? So this would be F1 minus F2 I. So that is why we have this F1 minus F2, right? Okay, so this thing is there. Now let us find out what would be F1. So let's write this thing in here. F1 is K, Q1, Q2, that is Q and Q, and separation. Separation is 1 plus X whole square. Right?
Yes, sir.
And F2 is what? This is K. Charge is also same. And then this is 1 minus X square. So this is the Coulomb force. So we have used the idea of Coulomb force. We have used the idea of equilibrium, right? Those two concepts in this question we have done. Right, clear?
Yes, sir.
Okay, so now the only thing which is remaining that we have to prove. So let's make a target. Let's make a target and let's think that what is the goal or what is the end result that we have to reach. So we have to see that the particle execute. So this particle will execute simple harmonic motion. So it will move right to and fro, right? Which means that the force on this thing should be what? If it is showing SHM, then what should be the force at this charge?
0.
That would be equilibrium. So that would be stationary, right? If the force is 0, then it
Yeah.
would be stationary. So, but it is showing SHM. We have already seen, you have told me that if something shows SHM, then force is what?
Proportional to the distance.
Yes, minus of it. So this is important. This should be always opposite. So this is the thing that we have to show, right? Clear? This is the goal.
Yes, sir.
Okay, so let us try to find that out. So F1, let's put this value. F1 is KQ square by 1 plus X square and minus KQ square 1 minus X square. So this is 1 plus X, 1 minus X. If we take the LCM, this becomes 1 minus X square and then whole square. Now KQ square is common. We can take it outside. 1 minus X square is here. So this is 1 minus X square. And then this is minus of 1 plus X whole square. right? So what is this thing? So this is kq square by 1 minus x square whole square. And then this is 1 minus 2x plus x square and minus of 1 minus of x square and minus of 2x, right? Because this minus is there. So x square cancels, 1 cancels. And what do we get? We get kq square minus 4x divided by 1 minus x square. And now we have reached this point. So this is our F. This is our force. Now you see that what is the condition? What is the limit that they are seeing? That x is very, very small than 1. Right? If you have 10,000 and then you have 1. So if you take 10,000 square and subtract it to minus 1, so you can write this thing as 10,000 square. Can you do that?
Yes, sir.
So similarly, this x is very small, 1 is very large. So what we can do in here? We can neglect this thing. Neglected because 1 is very, very large and x. Clear? Yes, is it clear?
Yeah, yes, sir.
Yeah, so and please if you have any doubt, please let me, yeah, please ask me. So now you see that this is minus 4 kq square and then x. So all these are constant. 4 kq square and whatever this thing, this is a constant, right? So I can write this thing as minus of cx. So what I'm getting, F net is directly proportional to minus x. What kind of force is this? What kind of force is this?
SHM spring.
Good. So this is an SHM. So now you see that, if we displace, so this was the initial case. If we displace this thing for a very small distance, for a very small distance x, then this will show, this chart will show an SHM, and this would be the behavior, right? So this is the
Yes,
thing
sir.
that we get. Okay, and if we compare this thing, so this C is, if we compare this with the original thing, so F net is what? Minus kx, right? This is SHM, right?
Yes, sir.
And we know that this k is how much then? This k is, then this k is 4k. Okay, this k is different. So this, let me write it as q square. And this k, we can write it as, right, what is this k? With corresponding to this angular frequency. So we know that omega square is k by m. Right, so k is m omega square. Correct?
Yes, sir.
So this k is m omega square, and then this is 4k and q square. So we can calculate this omega square as 4k q square divided by 2. So this is the equation that we had to calculate, this omega, which is 4k q square divided by 2. So this is the thing. So this q, we can take it outside, and then this is 4k divided by 2. So, and then yeah, we can also take this 2 outside, or let's keep this 4. So you see that what is this thing? So you see that what is the value of this k? Yeah, what is this k value? Which is 1 by 4 pi epsilon naught.
Yes, sir.
9 into 10 to the power 9, right?
Yes, sir.
So this Q, and what is the Q value that they have given? So Q is, charge Q is lying at the midpoint. Okay, if Q square is 10 Coulomb square. Okay, so Q square is given. So we'll put this value, right? And so let's put this value Q square, which is 10 C square, right? So let's put this through. Okay, and mass is 1 milligram. So we should not take this thing outside. We will put this value. So this is Q square. So 4, 9 into 10 to the power 9. This Q is 10 C square divided by mass is how much? 1 milligram. Right. Mass is 1 milligram. So we put the value of mass. So this is 1 milligram is 10 to the power minus 3. Right. So then this becomes how much? So we have this is 9 and 1. This is 10 to the power 10. And 4 and 9. So this is 2 into 3. And then this is how much? So this is this okay, this is 10 to the power 10 plus 30 or 3. I guess this should be, so this is 3. Are they seeing 10 square? Is this 10 whole square? Okay, so let's check that, because yeah, is this 10 square? What is it? If it is 10 square, so then this becomes this is 10 and then this is 30. I guess this should be 10 square. I don't know why they have written it like this, but this should be 10 C whole square, right? This is looking like, so this should be the, right? Okay, so then what is this thing? Then this will become, so this is 11 and then this is thing. So this is 14. Oh, what has happened? Okay, so why this is not working? Yeah, I will write this as 14. So this is 10 to the power 14. So this will become 10 to the power 7. Right. And then this would become how much? So this is 6. And then I can write, so this is 10 to the power 7. If I take one 10 from here, right? Or let's say I take this thing. So this becomes 10 to the power 5. So this is 600 I'm getting. So I'm getting 600, but the answer is 6,000, right? The answer is 6,000. Where did I miss 110? So 1 milligram, right? This is 1 milligram, and then where is, yeah, so this is 9 into 10 to the power 9. Okay, and then, yeah, so this is F is minus kx, this k is this thing, 4kq square. Did I miss anything? So this is 4kq square and x. So this is all. Yeah, so this is, so this is 2 into 3, and then this is 11. 9, 2, and 11. And then Okay, so what is happening? This is 14, so this is 7. So this answer should be 600, right? If I'm doing it correctly, so this answer should be 600, not this 6,000. So there is something wrong in this one. Okay, is this thing clear?
Yes, sir.
Yeah, so there is one missing 10, right? Because the answer is written in 10 to the power 5 radian per second. So what did we got? We got 10 to
Is
the power 7. So
yeah.
if we take 10 to the power 5 from here, so two zeros would be remaining, right? So two.
So what if in like such a question comes, we just have to write 600 into 10 raised to 5?
Yeah, because we have to compare it with, you see, we have to compare it with, so they are saying that its angular frequency of oscillation will be dash 10 to the power 5 radian per second. So they are writing it 10 to the power 5. So we have to extract, let's say that this is x into 10 to the power 5. So what did we get? We have got we have got 6 into 10 to the power 7. But the answer is x into 10 to the power 5 radian per second, right? So we take out 10 to the power 5 from here, right? We take out 10 to the power 5 from here. So this would be, there would be two zeros remaining, right? And now if we compare with x, so what is this x? X is 600, right? Is it clear?
Yes, sir.
Yeah, so because they have already written that the answer is 10 to the power 5 reading per second. So this x we have to find. So this x would be just 600, right? And I will check if there is some order misplacement, right? So this is 9 into 10 to the power 9, and then 9 to 11, 11, 3, 14. So this is 14. Or if this would have been 10 and then 13. So, okay, so then it is also, yeah, so then this should be 600 only, right? Not 6,000. So let me check this thing again. Yeah, so this, did I write it correct? So F is minus Kx. So this is MA is minus Kx. So K by M is omega square. So K is simply omega square M, right? M omega square. So I have put this K as M omega square. Then omega square is simply 4kq square by M. And then we just we put all these values and then we take, yeah, so this is correct. This is correct. Please note it down. And if you have any question, please tell me. Please note those things down. Yeah, please note those things. And this is the question. Yeah, so whenever you want me to scroll down the screen, please tell me. If it is 100, then it would be, if it is 10 only, then what happens? Yeah, whenever you want me to scroll down the screen, please tell.
Done, sir.
Okay, done. Yeah, so then please note down this one. Okay, so I got now. Yeah, so yeah, please note up to this point and then I'll tell you the correction, right? So mass
So what's
is,
the correction?
yeah, so you see that mass is given in milligrams and I have only changed it to, so this is correct. This should be, so this is correct, which is 10. And mass is in milligram, right? So this is 10 to the power minus 3 gram. And we have to change it in kg, right? So this would be minus 6 kg, right? So mass, we have to write
Yes,
it
sir.
in kg, right? So this would be, this is 10 and this is minus 6. So this is minus 6. So what would be the 10 powers that we will get? So this is 9 and this is 10 and 10 and plus 6, 16. So this would be 8. So if we take 5 in here, so this would be 1000. So this would be 6000. So this is
Okay.
right. So one order mistake and the answer becomes incorrect, right? So this is, yeah. So this was the one mistake. We were taking milligram, but yeah, we have to change it in kg. So yeah, there you have, what was the part that you have noted?
No, sir, I noted all of that. I just have to note this
This one.
a bit more up.
Yeah, is this okay?
Yeah, yes, sir.
Yeah, so please note it down. And whenever you have noted, we'll do the next question. So the next question would be on equilibrium, right? Yeah, whenever you have completed noting it down, please do.
So can you go down?
Yeah, so this is right. So this is 8, and then this is 1000. 6. So it was given that Q square is 10 Coulomb square. So this is 10. That was 10. And then mass was 1 milligram, which is 10 to the power minus 6. And this K is 9 into 10 to the power. So all these values we have
Done,
to
sir.
get. Yeah, good. So now let us do a question on equilibrium, right? And remember that there's another question. So I will give it, yeah, I will give it as your hint. So this is the question that time, and I will give you also the hint. So let me just erase this part. So you please try this question, right? So in the earlier case, what did we do? We had these three charges, and we placed or we displaced this charge at this position. So this was the x displacement, and then it followed the simple harmonic motion, right? Right.
Yes, sir.
Now these in the second case, what is happening is that you have all these charges again, right? And this charge, you are not displacing it in this direction or in this direction. You are displacing it in this direction. So then we have to show that it will again behave, it will also follow the simple harmonic motion in this direction. So now it will follow the simple harmonic motion in this direction. Clear? Okay, how many people have joined? Should we join some? Room? Okay, so now this is the displacement that it is happening, right? And we have to show that again, the force would be, the net force would be proportional to, or this would be minus k. So if we want to prove that if we displace this charge at this position, this is the x distance, right? This is the x distance that we are displacing. And then we want to prove that this charge will follow the simple harmonic motion. So this charge will go in this part, and then it will move to and fro. So this will follow the simple harmonic motion. And how many contributions would be there? How many contribution would be there? If we draw the free body diagram, how many contribution would be there?
3.
3. There are only 2 charges, right?
Yes, sir.
So let me draw this thing, right? So let me draw the effective diagram. You have already understood about the effective diagram of this thing. So if this thing is clear, then this would be clear for you, right? So now let's say that we have displaced this thing in here. So this charge is in here. It was in the early case, it was here. Now it has gone here. This displacement is x, right? Now, if we calculate the force, so what are the charges? 2 electrons which are fixed at a distance 2d. So these are 2 electrons. So minus E and minus E. And this, let's say this is D, right? This is D. A third charge proton. So this is proton. So we have displaced this proton slightly by distance perpendicular to the line joining the two fixed charges, right? Proton will execute simple harmonic motion having angular frequency. So you have to find out this angular frequency, right? This is the proton. This is proton. So for this proton, if I calculate the force experienced by this proton, so how many contribution would be there?
3.
There are two charges, right? These two electrons. So one would be coming due to this thing, the other one would be due to this thing. So this is looking like the dipole, right? But in dipole case, we have two different charges, but we don't have two different charges in this case, right? So we only have the similar charges. So we have to calculate the net force. Net force would be superposition principle, right? So let's say
Yes,
that, yeah, so let's say this is 1, this is 2. So due to this charge, the force would be away. Let's say this is the line. These are the straight lines. So at this point, this is the proton, which has, right, so this is the proton. And due to this electron, the force would be away or towards its side. What would be the force? Towards or away?
away.
This is proton, this is electron. Both will attract.
Which ones are 1 and 2, right?
No, no, not 1 and 2. I'm talking because at this point we are calculating. F net we are calculating at this point.
Okay, yes, sir. That's towards each other.
Yeah, so this would be F1 and this would be F2.
F2, same towards.
Yeah, again same. So now we have to find out, and you know that these are vector addition. So then we have to use the resolution of vectors, right? Resolution of vectors. And for that, we have to consider that this is a theta angle. So this is a theta angle. If we draw the parallel line, so this would be, right, this is parallel. So this would be theta. And this is parallel, so this would be theta. Right. So what would be this component? Can you tell me? What would be this component? Let me see if you remember or not. What would be this component? This is the vector.
So could you show which component?
Yeah, this one.
K.
This is the.
No.
So F1 is yeah, F1 is this thing, right? This is F1, which is at this angle theta. So what would be this horizontal component? What would be the vertical component?
Yeah, horizontal will be cos theta. F1 cos theta.
F1 cos theta, right? And this would be F1 sin
F1
theta.
sin theta.
Again, let us see here. So this component would be what?
F2 cos theta and F2 sin
F2
theta.
cos theta,
So,
and then, yeah, F2 sin theta. So you see
so
that,
F1 equal
yeah. And yeah, we also know that
F1
the
sin
distance,
theta
yeah,
equals
yeah, distances are same, right? So let's say this is R, this is also R. So magnitude of F1 and F2, they are same. So this will cancel with this one. So F net would be how much? F net would be minus of F2 sin theta. Why am I writing minus? Because this is the displacement that we have written. The displacement is this, but the force is acting downwards. So this is minus F2 sin theta. Is it clear?
yes, sir.
And how much is this thing? So F2 is K and E square divided by how much? R square. R is, let me write it as R. And then what is sine theta? Sine theta is, this is theta, so sine theta is P by H. Perpendicular is X, H is R. So this is minus K E square X divided by R cube. R is what? R is root of X square plus D square. And we know that X is very small. So this thing is how much? So this we can write it as minus E square X divided by X square plus D square and 3 by 2. So X square we can neglect and square will cancel. So this is minus K E square X divided by DQ. So this is F net. And if we solve this thing, so F net is directly proportional to minus 6. So this will show what? What will it show?
Spring force.
So a spring force, this will show SHM, right? So let's say,
Yes.
yeah, let me, yeah. So let me tell you what is happening. So let's say that these two charge are placed, right? So let's say these are the two electrons, and then in between you have this proton, and you displace this proton in this direction. So then it will show SHM, and this will go down and then up and then down and then up. So it will show SHM, right? This is what is happening.
Yes, sir.
Yeah, so, but in the earlier case, what did we saw? In the earlier case, these were the two charges, and in between we placed this charge in this direction. So then it showed this kind of oscillation, right? So if we displace it right direction, so it will show this kind of oscillation. But in this question, we have this kind of oscillation, right? Okay, so is this question clear to you? So these are two electrons, right? And then in between, this was the initial position of the proton. So you displace this proton at this position. This is the proton now. And then it will show SHM. It will go downwards, it will go upwards, and then it will show SHM. So this is what is happening. Is this question clear? Yes.
Yes, sir.
Yeah. Now the question was, we have to find out. I did this question in here. I was supposed to give it as your homework, but I got carried away, and then I did this problem, right? So okay. So we have this thing, right? We have this thing, and what else? So this is what we got. F net is this thing, and this is showing SHM. So if we compare it with the coefficient or constant, F equals to minus Kx. So this this small k is this K, capital K E square by dq, right? And this is m omega square K E square by dq. So omega square is how much? Omega square or omega is root of K E square divided by m dq. So this is okay. So we have this right. So we have to write this K as 1 by 4 pi epsilon, right? So okay. So there is this Q square. Yeah, Q square divided by 2. Why we are getting this 2? Right, why we are getting this 2? So the whole distance is 2. Two electrons are at a distance 2d. A third charge is this thing perpendicular, and then this is g square. So yeah. Oh, so there was this 2 also, right? So there was this 2. So this is 2, and this key is 1 by 4 pi epsilon naught. So let me write it in here. I don't have that much of a space. So this is 2, and e square divided by m 4 pi epsilon naught dq. So this 2 and this 2 cancels, and the answer that we get is e square divided by 2 pi epsilon naught m dq. And why did we get this 2? Is it clear? Why did we get this 2? Yes. Why did we get this 2? Is it clear?
Because yes,
Why did we get this 2 then? Please tell me. Why did we get this 2? Yeah, please look at the diagram.
yes, yes,
So,
because
so
there are
yeah,
two f1 sin theta and f2 sin theta, so it's
yeah.
2f sin theta.
Yeah, so that is 2f sine theta. That is why we are getting this 2. So that part we missed. And then this would be the frequency. If we compare it with the angular m omega square, so this would be the frequency. So the answer is this one, right? This is the answer. So if this is clear, please note it down. And then this was supposed to be your homework. So if we make this diagram, then the whole answer would be complete. But yeah, please note it down. So yeah, please note it down and then try this on your own as well, right? So try this question now on your own, and then it would be really helpful. And whenever you have noted that, please. Yeah, whenever you have noted, please tell me. Yeah, whenever you have noted, please tell me. So distance between them was r, right? And this is a triangle. So this was x, this was d, so r was hypotenuse. So x square plus t square. Yeah, whenever you have noted, please tell.
So should we write the next question? The identical small charged that one?
Yeah, which question?
The two identical small charged spheres, each having
No, no, no. So this,
a map.
yeah, this one we'll do next time, right? But yeah, have you noted down this part? So this is the
No,
thing that
sir,
you.
I have the last part.
Oh, yeah, this is the thing that you have to know, right? Because this is the question that we are doing, right? This is the question.
Yeah.
The question is this one, and yeah, I didn't have any space, so that is why. Let me just. So this is the thing that you have to know, right? So from here to, so this is, yeah, this goes from here and then here, and then you calculate by comparing the one. So after this one, you have list. Whenever you have noted, please tell. And if you have any doubt, please tell me. I will repeat this thing again. So please don't hesitate to ask me, right? I will repeat this thing if you have any doubt.
Done, sir.
Done. Okay, so now let us we have 5 minutes more, so we can do one question. And yeah, you already saw this thing, so let me just let me bring this question in. So, so this is the question. Two small charge spheres, each having a mass m, hang in an equilibrium as shown in the figure. So I will draw the figure. The length of each string
Sir,
is
can I write down the question and can we do this in the next class?
okay, sure, sure. Yeah, you try this question. And in this question, we have to
Yeah.
use the idea of Coulomb's law, right? Coulomb's law. So just note down, not just note this thing above. So Coulomb's law plus,
So majorly Coulomb's law, right?
yeah, equilibrium, and then we have to use tension. So these are the three concepts that we have to use, right? So this is a mixed problem, right? Yeah, just note down this question and then we'll do this in the next class.
Done, sir.
Okay, so yeah, we'll stop here and then Yeah, see you in the next class, right? And always revise all those portion, right? So those concepts that you are studying in the CBSE portion, just revise them, right? So yeah, because those have
Yes, sir.
important derivations, right? You have Coulomb's law derivation, you have electric dipole derivation, right? And then you have superposition principle derivation. So all these derivations are there, right? And what is the current topic that you are doing? Have you started Gauss law, application of Gauss law?
Yes, sir. Not application. One second.
Electric flux, what about electric flux? Have you started electric flux?
We started torque, sir.
Oh, so torque you are doing. After torque, it would be electric flux. Okay. So I guess yeah, I've started Coulomb's law and then electric field and then torque. So yeah, we're not that far. Okay, so we will simultaneously go along with the CBSE portion and then yeah, we'll be. So this will be the case. Okay, so yeah, we'll stop and
So
see you. Yes.
this year we